Yeah. Now it's recorded. Yeah, thanks, Dr. Maha, about this. I wasn't paying attention. Yeah. Okay. So it's a plus for those who attend the sessions. Okay. We can start from here. From yeah, we can start from here. Swap test. Swap test is one of the ways to calculate the inner product using quantum circuit for the quantum kernels. Okay. It uses an auxiliary qubit initialized to 0 and then two encoded states. The first set is an encoded state of one data point in the dataset, and the other is another data point in the dataset. We will get the inner product or the similarity between them using quantum circuits, apply Hadamard on the first qubit, then apply Redkin gate, then apply another Hadamard on the first qubit, then we measure. Okay. So the initial state is 0, get psi, get alpha. We apply Hadamard. It will be 1 over square root 2, get 0, get psi, get alpha, plus 1 over square root 2, get 1, get psi, get alpha. It's a normal Hadamard gate. So we apply the Friedkin gate. The Friedkin gate is a controlled swap gate. So this term stays the same because it's this auxiliary qubit is 0. This is 1. So we will swap these two states. It will be like that. So we apply Hadamard again on the first qubit. Two states will give us 4 terms. Then uh, we'll, we'll group the 0 out of these two terms. It will be get 0 and half. It's just like taking a common factor, so it's not that hard. Half get psi, get alpha plus get alpha, get psi. So this step is clear for now. Okay. Then we want to get the probability of 0. We knew this. If we want to get a probability of a certain state, then you square the amplitude of this state. So this whole term is the amplitude of state 0. Then we square it to get the probability of 0. 1 over 4, the norm of this whole state. Get psi, get alpha plus get alpha, get psi squared. So this is a normal way to get the probability of the auxiliary qubit being 0 when we measure. So is it clear for now? Okay. So to make it easier, while we are doing our proof, we'll say get psi, get alpha is A, and get alpha, get psi is B. So probability of 0 is 1 over 4, the normalization of A plus B squared. So this is a normalization factor. Okay. I hope it's clear for now. So there is this rule. It's called expansion of squared norm. When we are getting the norm of a summation of two vectors, it can be expanded into 4 inner products: A inner product B, A inner product A, B inner product A, and B inner product B. We all knew when you have inner product uh, with two similar states, it will be 1. So this is 1 and this is 1. So we will calculate what is actually inner product A, inner product B, and B inner product A. So we will take the inner product between A and B, and we will input the A. A is Here A is a bra A, which will A we knew it's get psi get alpha. So the bra of A is get psi get alpha. Uh, bra psi bra alpha. So it's the way around. I have reversed it. Alpha psi. So this is a kit A and this is bra A. So we have replaced the A with bra alpha, bra psi, and B is um, kit psi, kit alpha from here. Okay, so this state is a tensor product between alpha and psi, and this state is psi tensor alpha, and we want to get the inner product of two tensors. So is everything clear until this point? So we want to get inner product between A and B. So it we ends up with an inner product between two tensors. Okay, great. So uh, there's a second rule which called tensor product inner product rule. If you have an inner product between two tensor tensors, it can be two inner products. It's like alpha tensor psi inner product psi tensor alpha. It can be the other way around, psi inner product alpha tensor psi tensor alpha. Okay, so we end up with this state. And we knew the inner product is a similarity check, so it's a scalar value. So it doesn't matter if it's alpha inner product psi or psi tensor product alpha, it's the same. So it will be the magnitude squared of the inner product of psi inner product alpha, or the other way around, alpha inner product psi. Okay, so we found out that the inner product between A and B, it's an squared inner product between psi and alpha. And with the same steps, we will find that inner product between B and A, it gives the same results. So till this point, is there any questions or any things that is unclear? Okay, great. So with this information, we get A inner product B and B inner product A. We will use this information to get the norm of A plus P. A, this is 1, this is 1, and this is this value. So we take 2 as a common factor, and it will be 1 plus magnitude squared of inner product psi alpha. And we knew that probability of 0 is 1 over 4 this norm. So replace this norm with this whole term. It will be 2 and 1 over 4, it will be half, and this whole term. So we multiply both side by 2, and 1 goes to the other side, -1. So what we want is the inner product between psi alpha is actually 2 times probability of 0 minus 1, which is from the from the previous session, it is expectation value in z basis. So what we found here, that with this method swap test, when we input two encoded states, which is two data points, and we do this whole steps and we measure for number of shots and we calculate the expectation value. This is the inner product that we will input into the matrix itself. So we can say the element in the kernel matrix, which is the encoded state. Here, the symbol means the encoding, the en the encode state of xi is it's a data point in the dataset, and xj it's another data point in the dataset. We encode them in quantum circuit. The Sorry for the connection. Uh, have you heard what I have said here for the quantum, for the kernel part? So I was saying, if I want to calculate an element in the kernel matrix, which is two states, we encode it. Can you hear me now? Sorry for the connection. I hope you can hear me. Okay. If I want to calculate an element in the kernel matrix, which is the inner product between two data points, we encode them into quantum circuits, quantum states. Then it's the expectation value in z basis. So it's clear for now for how what we are doing here, how we calculated an element in the quantum kernel.
Yes, can you go with an example?
Okay, let's say I have data set with only two features. So how the circuit would look like? It would be two qubits uh, for the encoding. Here I have used any encoding or any type of encoding. If I have used, let's say, amplitude encoding, I would only need one qubit. As you know, one qubit can represent a data with two features. But here, for I have used two qubits as I have used in this diagram. Let's say an encoding type like angle encoding, which uses n qubits, n features. So let's say I have data with two features, then I will encode the first data point, then the second data point. So the circuit starts with encoding the features first with any encoding type, then apply Hadmard on the auxiliary, then apply the Friedkin gate. Friedkin gate is swapping the two states. So first we swap the first, let's say, first wire with the first wire, then the second wire with the second wire. So we have swapped this state with this state. And then we apply Hadmard and then we measure. So as we see, we need, uh, if used an encoding method that uses n qubits, n qubits, which is n features. So it uses the number of qubits as the number of features, which like angle encoding, z feature map or zz feature map. This method uses n qubits, n features. you will need for this swap test 2n plus 1. N here is the number of features. Okay, so we create the circuit for each element in the kernel matrix. So the kernel matrix we knew it's a d by d. D here it's the number of samples of the data in the data set. So if we have 100 samples, we will create a 10,000 um, unique quantum circuit. But we knew that the quantum matrix is a symmetric, so we only need half of that. It's the lower triangle, so we'll create 5,000 unique circuit. So it doesn't actually depend. The computational cost is only d squared. So the number of features doesn't actually affect the computational cost here in theory. Uh, So this is the swap test and how it's done. Of course, it's very expensive. The freaking gate is actually very expensive. If you knew that swap gate, can anyone tell me uh, the swap gate itself, how many C nodes it needs to represent a swap gate?
I guess it's a 3.
Yeah. Okay, great. For the swap gate, it's actually decomposed into 3 C nodes. Okay, 3 C nodes. So imagine the swap gate itself is controlled. So we need to add controlled for each C node. So it turns into Toffoli gate. So can anyone tell me um, how many C nodes in one Toffoli gate? Okay. Um, if you decompose one Toffoli gate, uh, it it uses 5 to 6 2-qubit gates, which is C nodes, and other 1-qubit gates. So let's say one Toffoli gate uses 6 C nodes and 18 C nodes, and this is only one controlled or one Friedkin gate. So let's say I have two in this case, so it takes 36 2-qubit gates, which is CNOTs, which are CNOTs. So it's an expensive method, but it's very effective in theory. We only measure 1 qubits, and we don't need many shots to get our answer. So this is swap test, and this is one of the simplest proofs to get the inner product and similarity. Okay. Is this method clear? Do you understand? Yeah, like 80% of it or 90%? Okay. So this is the first method to calculate the quantum kernel matrix. Second method is Hadamard test. It's a more complex. Guess we can use. I guess we can use few qubit by theory using a good encode. Yeah, that's true. But you know, in the task, when I have told you to search about how you can initialize a unitary metric for amplitude encoding, and all of you have said it's an expensive way to initialize a unitary matrix. So if you want fewer qubits, you will sacrifice the complexity of creating the unitary matrix for the amplitude encoding, which is the depth and many gates. So it's a trade-off in our NISC era right now. So maybe in the future, fault tolerance quantum computing, it will be a different case. So, but it's a great way of thinking to make or limit the number of qubits. Okay. For our case Hadmard test, I need you to search and read about Hadmard test and compare the differences between the Hadmard test and swab test. It's a more complex approach. I don't want you to write a full proof of it. I just want you to read about it, research, compare it between the swab tests, just to ensure that you have read about it. Okay. Okay. This is your first task. And the third method and most common method to calculate the inner product between two features is called compute uncompute method. As you see, it's a very simple circuit. It only uses encoding method. This is an encoding technique. Any encoding technique, base encoding, angle, amplitude, Z feature map, any encoding, and then on one data point, and then we apply the adjoint or the dagger or the inverse. This is all the same. Encoding for the second data point that I want to inner product with. So this case, we only need two encoding techniques, and then we measure all the qubits. So it's an expensive on the readout error here. We measure all qubits, and it depends on your encoding method that you have used. If you have used, let's say, angle encoding, it will be much simpler, but it won't capture complex patterns as there is no entanglement. But let's say if you have used the Z feature map, it will give or capture more pattern in the data or similarity. So it depends on the encoding that you use. So uh, does anyone does anyone here knew how the dagger works or how to do the inverse of the encoding? Can anyone raise their hand and say, explain it to the other mates? You can go, Ala. Ala, can you hear me? If you want to explain it to the other colleagues, you can.
Uh,
Oh, yeah.
I just can't explain it right now because I don't know how to explain, you know.
Okay. So let's say um, I have this unitary matrix which is Hadmard, Z gate, NOT gate, and Y gate. So the dagger is the same gate but reversed. So it is Y, then NOT gate, Z gate, and then Hadmard. So when you apply Y and then Y dagger or adjoint, it will be unitary at the end. So this is the dagger part. You apply the inverse of the matrices and reverse the order. As you can see, the inverse of Hadmard is also Hadmard, the inverse of these, because this called Hermitian operators. So let's say I have a rotation gate with theta. The adjoint is negative theta. Or let's say I have another gate which let's call it W, for example. If I want the dagger, I need to calculate inverse of it first. So this is how you get the dagger part. You first reverse the order, then do the inverse for each one of them. Okay, is it clear? Maybe we can, in our example, it will be clearer. So it's a very simple approach. Apply encoding method on xi, then apply the inverse of that method. It has to be the same method. You can't just apply angles and apply the feature. No, it's if you have chosen one encoding method, you have to choose the same encoding method for the other data point. Then measure all qubits. Okay, to get the same inner product between these two encoded data points, it will be equals the probability it being all zeros. So let's say I have run this circuit for 100 shots. I will calculate the probability of it being all zeros. Then this is the value to input in the kernel matrix. So it's different from the swap test. For the swap test, we calculate the expectation value in the base 1 qubit. Where is the circuit? Here, only 1 qubit. But for compute and compute, we need to measure all qubits, then run the circuit for many more shots to get probability of it being. Then this is the value we'll input in the kernel matrix. So I need you to also read about the proof compute and compute method. It's if you have understood the proof for swap test, it won't be hard for compute and compute. Just yeah, yeah, read Ala. Can you hear me, Ala? You have raised your hand.
I'm sorry, I was talking and the mic was off. Yeah, I was
Yeah, yeah,
saying like
yeah.
I was saying like can we use the this method with the Grover algorithm and the Shor algorithm, like the inverse unitary gate?
Um, can you be? I don't actually understand the question. So you're saying we can use Grover algorithm besides or with the uncompute method?
Yes.
So what's the motivation behind this integration between these two?
Like when I was working on a TSP problem, I used a different encoding method, and especially with the unitary dagger circuit gate. So it gives it speed up, and at the same time the complexity was low somehow.
Um, Actually, for our case, for the compute and compute method, for compute and compute method, we need the probability of all zeros. So there are some papers and work about using Grover algorithm or any amplification, amplitude amplification to amplify the state of all zeros, so we won't need as many shots. So this is one way to use Grover algorithm in our case.
Okay, can you share these papers? I'm really curious about this.
Okay, no problem.
Okay. Thank you.
Okay, so I need to read about the proof. Read about the proof for the method. So this is two tasks for the quantum SVM. So this is about it for the quantum kernels. You will use one of these three methods to compute the quantum kernel. Then you input the quantum kernel into the functions as the classical workflow. So it's a hybrid approach. The quantum helps us with calculating the kernel to get a different capturing a different patterns similarity between the data and to leverage solution and entanglement. So we'll talk about some other encoding types. The Z feature map, how it's done. We use if n features, we will need n qubits like encoding. So first we apply hard on all qubits, then we apply R Z rotation gates, and then we apply a controlled Z gate. So the controlled Z gate, which is it, when we see this gets a control Z, which means for the state which is all ones, it change the phase from if it's positive, it will be negative, and if it's negative, it's positive. So it's just give it a taste of entanglement. So it use apply Hadmard on all qubits, then rotation in z-axis on all qubits. So the angle for the rotation z, it's, let's say if I have this is one data point, I hope you can hear me now. The connection is not great right now.
Yes,
Okay,
it's okay.
sorry for the connection. Yeah. Is there any
No,
questions? Is there any?
no, we were talking about the Z feature, I guess, and the rotation.
Yeah. For the Z feature, I was talking about applying Hadmard on all qubits, then apply rotations in Z basis. So what are the angles for these rotation gates? So let's say I have this data point with n features. Um, then for each, um, let's say each value in this data row, I will input it directly into the rotation in Z basis. If you know, in our previous session, for the angle encoding with the Rx and Ry, uh, the first thing to do is to map the data into negative pi and pi. But it's a special case here in our Z gate, as it doesn't. If you use a gate, it's only phases. Um, so it doesn't have the cosines or sines in this rotation gate, so it isn't bounded in this range. So we can input it directly. So if it's, let's say, 0.1, zero point 0.2, 3, -5, we will do RZ with zero point 0.1, RZ with zero point 0.2 directly. So there is other um, papers or work, it multiplies the value by 2, as in the gate itself, the value is divided by 2. So it doesn't do much. It isn't much of a difference, but you multiply by 2 to match the papers or the related work. So we apply hard gates on all qubits, then we inject the values for the data point into rotation Z gates. So this is one way of encoding Z feature map. There is a more complex way, more better way. Can you send us? Um, okay, no problem. It will be in the materials in the classroom. Okay. There is another more effective way to encode the data, which leverages superposition and entanglement. If you take a look at the Z feature map, you will find that there is no entanglement. But for the ZZ feature map, it uses another gate, which is called RZZ gate. Which, when we decompose it, it's a C naught, then a rotation RZ gate, then another C naught. So this is called RZZ gate. So it uses the same n qubit for n features, and the RZZ state, it's like a staircase. So you apply RZZ state, it's a 2 qubit gates, as it's in the diagram here. So you apply it between qubit 1 and 2 and 2 and 3, and it's like a staircase. So uh, for here, it's the same as Z feature map, the same injecting of the values into the rotation gates. Then for the RZZ, what are the values that we will input here in this RZ gate? It will be pi minus xi. Xi, it's value of one of the data points. So if it's between the first two, it will be x1 multiplied by pi minus x2. Also, the same for the RZ, papers will multiply by 2, as I have said, as the rotation gates in as the rotation RZ actually have the value divided by 2 inside the matrix itself, so you can divide by 2. Okay, so now when we have the knowledge of how this two type works, um, if you take a look, this is a simpler approach. So this is a simpler approach. It leverages the superposition and phases to encode the data, but uh, it's good for our NISC era. The circuit, it's not that deep, and it doesn't use that many 2 qubit gates, so the error rate won't be that high. For the ZZ feature map, it's more complex. It captures the relations between the features itself by leveraging the entanglement. So this is most two common ways: Z feature map, ZZ feature map. Okay. For our third task of the day, um, I need you to read about the Pauli feature map. It's a more complex encoding method. It's very hard to do it in our quantum circuit or quantum hardware state right now, but it's very effective for encoding the state. It leverages superposition, phases, entanglement. So it's a very great encoding method. So I need you to read about it and do some research. Okay. So this is a small comparison between swap test and compute method. Uh, this compute and compute only need n qubits. It depends on the encoding types, of course. If you use amplitude encoding, it will need log n qubits. For the swap test, it requires double the qubits that required for the compute and compute. Here, as shots are very low compared to the compute and compute because we only measure one qubit. But here in our case, we measure all qubits and we need the probability of only one state. So let's say if I have 10 qubits, then I need much higher number of shots to get a good approximation of the inner product. So it's another trade-off for the number of qubits, the depth of the circuit, number of shots. So this is the lecture. Is this comparison clear? Is there are there any questions? Yeah. Go ahead, Dr. Matt.
Uh, Thank you, Abdurrahman, for the good talk. I have a question regarding the Z feature map and the ZZ feature map. I know it's a kind of data encoding, right?
Yeah.
But does it use a kernel trick to reduce the dimension of the features or to categorize the data somehow? I don't know because I've used it before as a data encoding feature, but I don't know if it also uses a kernel trick or not.
Okay. Let's say for this Z feature map, it's a similar approach, and we have these two vectors. Let's say x and y, two vectors. Each vector, let's say, let's make it simple, two features only, x1. I need to get the inner product between x and y. So for the compute and compute method, I will first encode the x into using the z feature. So you need two hardmarks. Then the rotation, see, with x1 and rz for x2, and then controlled z. So this is the first part. I have encoded the let's say vector x into quantum circuit. So the second part is applying the same encoding, but the inverse of the z feature map. And for the y, the inverse will be starting with the rz. It will be the same here, yeah, rz, and then negative y1, and the same with the rz negative y2, and then apply Hadmard. So here we encoded the x vector, and here we encoded the y vector with the inverse of the z feature map. So it's clear for now. So if you take a look at if you take a look here, control Z and control Z, they will cancel out, and then have rotation Z and rotation Z, which is actually a linear operator. So we can say x1, it can be only one operator, which is RZ x1 minus y1. So we can replace this whole two state with only one gate, which is RZ x1 minus 1. And the same here. So it will be RZ x2 minus y2. So for the compute and compute in the background, this is what actually is happening. So it's only two Hadmars, and then rotations in z-axis with the difference between the elements, and then two Hadmars, and then of course the measurement at the end. So this is for the Z feature map. It is the same will be for the ZZ feature map, but it's more complex, as it will be more complex for the staircase. It can be done. I can do it right now to be more complex. Yeah. So this is what's actually happening for the compute and compute method. So,
Thank you. This answered my
yeah.
question. Thank you.
Yeah, we are welcome. Yeah. Okay, this is for the session. Then for the practical lab, let's say, okay, for the practical lab part, we'll be using a quantum support vector classifier from quantum machine learning library from Qiskit machine learning. It got an update last month, so it's a good thing. So we need here, this is all familiar scikit-learn, and from the Qiskit circuit library, we need the ZZ feature map. In our code, I have used the ZZ feature map. You can use the Z feature map if you want. And from primitive, there is sampler version 2, which is the simulation that we will use air sampler. And from Qiskit machine learning, state fidelities, we'll use compute and compute. And for the kernel, we'll use fidelity quantum kernel. There is other kernels. Fidelity quantum kernel here uses the simulator with shots. You can use another kernel, which is state vector quantum kernel, which uses a state vector directly. But in our case, we'll use the fidelity one, as we need the shots. From the algorithms, we will use the quantum support vector classifier. There is other hybrid approaches, but this is the simplest one for now. You can read the documentation or read about the quantum kernels. Okay, so this is the boards that we need. We will use the mnest data, which is data of the digits. We'll use the tabular data, which is one data point is a big array with 784 elements. So we will not use images or images for our case. We'll use the tabular data, and we only do only binary classification between two digits, 1 and 7. You can change as you want. In qubits, I have chosen 4. You can choose whatever you want. So we will do BCA, dimensionality reduction, from this 784 into only 4 qubits, and we will use 100 samples for training. So the kernel will be 100 by 100, and for testing, only 30 elements. So okay, our random seed here, so we can reproduce the same outcomes. First thing to do is loading the mnest data using fetch OpenML from scikit-learn. Then we get data, then we mask the data to get the 2 digits that we want. So then this method used to get the same number if we have 100 elements per class. So 100 element, which is classified 1, and 100 for the 7. Okay, great. Then we normalize the state. Here we divided by 255 as uh, one element in the array is actually considered as a pixel, or a grayscale pixel from 0 to 255. So we divided it by 255 to actually to normalize the state. Then we do the reduction to make 784 elements into features, into 4 features only. Then we split the training and test. Okay. Okay. Here, this is a ZZ feature map. As you have seen, the arguments feature dimensions is n qubit, which is 4, so it's 4 qubits. Here, reps, it's we can say it's how many of them I want. Let's say I 2 reps, so it will repeat the same encoding 2 times. So with the same gates, if we have taken a look, let's say there is no barrier here, so okay. B here, it means the phase, or it's the same as RZ gate, so it's not one. And then I want grow. Okay, cancel. Why we do them? You mean the encoding, the Z feature map? No, the reps. Okay. It I will just reverse it to 1, so you can. Okay, here this is the ZZ feature. Apply the hardware, then the rotations, then the RZZ, which is the, like I have said, C naught, then 2 multiplied by pi minus x0 multiplied by pi minus x1, and then the C naught. And we do it or with each pair of qubits, so it's a staircase. So this is the ZZ feature map that we have seen in the lecture. Is it clear for now? So it's nothing new here. Okay. So if we want, let's say a richer, so there's the layers. Yeah. So this increases the number of layers of the encoding. So if we want a richer representation of the data, we can increase the number of reps. Theoretically, it gives a higher readability of the data theoretically, but in practicality, or in real hardware, it uses many gates, so it gives a higher error rate. So it's not an advantage in the real hardware, but theoretically, if you're working in simulators, it gives a better results. So I have tried it; it didn't work for me. Okay, yeah. So let's say it's a fine-tuning process after that. So you try the ZZ feature map, then you try to change a number of qubits, then you try. It's like a machine learning task that you try to fine-tune the parameters to give the best results. Okay. Then we decompose. Then we decompose the ZZ feature map, and we draw it. If we didn't, decompose it, it will be look like that. This is the feature map. It's an abstract gate, and when we try to run the sampler, it will give us an error as it doesn't understand the instruction called the feature map. So you need to decompose it or to transpile it later on. So in our case, we will just decompose it as the transpilation process is a whole different it's a whole different thing. Yeah. Okay. We initialize our sampler, then we do the compute uncompute with our sampler, which we have just initialized. Then we call fidelity quantum kernel with the feature map. Feature map here is the ZZ feature map. We can use the Z feature map or even any encoding type. It doesn't have to be a ZZ feature map. So feature map with the fidelity. Fidelity here is compute uncompute. So we tell the quantum kernel that this is the encoding type and this is the method that we will be doing, and compute and compute we initialize the or the argument is the sampler air sampler, so it's a shots based circuit. Okay, then we initialize the QSVC with the quantum kernel that we have just initialized. So the process is initializing the sampler, initialize compute and compute, then the fidelity quantum kernel, then the QSVC. Then we treat it as normal as the other classical models. Fit with the training and the predictions testing, and the accuracy. It's like a normal model. So the accuracy here, it's 90%. It takes 13 minutes and let's say 14 minutes to complete the quantum kernel. In our case, 100 by 100 sample. So number of shots here is the default value, which is 1024 shots. We can change it. This is a classification, precision, and recall F1 score, and this is the confusion matrix. This is the first 20 training sample with this is the quantum kernel matrix. It's much larger, but it's here it's only showing the 20 training sample, and this is the testing. This is the true labels, and this is the predictions. It marks here the values that has been misclassified. And this is other matrix precision recall F1 score. So it's a simple model, and it's a powerful one. It all quantum kernels itself. It's not let's say it's not exclusive to only quantum machine learning. It can be used in other fields. So the idea is very powerful to use the similarity check using quantum circuits and algorithms to get the inner product between any two encoded states. So this code or this notebook will be in the materials. You can play with it, try different things, read the documentation, so you can read the documentation, so can you try different things, try different arguments, try different profiles. So let's say the task is to the task here, the practical task here is to increase the number of training and try different 2 digits numbers. Okay, great. So it's this is the task with the S task we have said. I just need to remember them. The first one is read about the Hadmard test and compare with the swap test. Read about the proof of compute uncompute. Read about the Pauli feature map. Okay. After that, uh, you go into the practical lab and then you try different digits, different number of qubits. Just don't go higher than 7 or 8. It will take a lot of time, hours, and try different number of training. So you just play with the notebooks. Okay. Are there any questions about the session today? Okay, great. So the materials, there is nothing better than 90 euro can get. You try and find out. I haven't tried any different parameters. So the lecture and the notebook will be in the classroom materials. The recording will be on YouTube next week, I think. And if there are any questions, ask in the WhatsApp group or the classroom. See you next week, inshallah.
Yeah, thank you so much for this session. I really appreciate it.